everything in the universe is attracted to me, and every other thing in the universe by this force of gravity. We think of gravity as being just a force that pulls us down toward the Earth, but really it's much more universal than that. Every object that has mass, and that's all the objects, they exert a force of gravity on every other object. So we think about the force of gravity as acting in pairs. Two objects each exert a force, an attractive force, on each other. Newton developed his law of universal gravitation, which not only said that all objects attract each other by this force of gravity, but also helped us to understand the amount of force that would be present there. Now, Newton would have just said that it's proportional to the product of their masses and inversely proportional to the square of the distance between those masses. We also have this gravitational constant, this factor that we multiply that by, and we can think of that as being a conversion factor between mass, the masses that we have, and getting us to forces in newtons. So this gravitational constant would have different values if it weren't force in newtons that we wanted, if we wanted, say, force in pounds instead. Really, Newton's law of universal gravitation talks about the force of gravity that exists between 2 points, not 2 objects that take up space. But we find that if these objects are spherical, then the equation works out to be the same way. Works out to be the same thing. So we're going to have the product of the two masses, m1 and m2. We'll divide that by r squared, where r is the distance between the centers of those two objects. And we'll multiply that by not the acceleration of gravity, but the universal gravitational constant, g, which we'll use as 6.67 times 10 to the negative 11th cubic meters per kilogram second squared, or alternate units for that, just using the abbreviation of newtons, meaning kilogram meters per second squared. We could write that as Newton meters squared per kilogram squared. That's probably a more useful unit most of the time, since we're going to want to calculate force in newtons, not in kilogram meters per second squared. So, as an example of this, let's write an expression for the force of gravity acting on some unknown mass, and we'll just say that this object has a mass m at the Earth's surface. So the distance between those two objects is going to be just the radius of the Earth. So we draw this out. We have some mass m, and then this is the Earth. And the distance from the center of the Earth to the center of that object, that's just going to be r. Really, it'd be a little bit larger than the radius of the Earth, but since the Earth is so large compared to any of the objects that might be on the surface of the Earth, we can just say that that distance is the radius of the Earth. We also need to know that the mass of the Earth is equal to 5.97219 times 10 to the 24th kilograms, and that radius for the Earth is equal to 6,378,100 meters, and that's an average, because of course we have high points and low points on the surface of the Earth, so that would vary a little bit depending on where you are. So if we want to know the force of gravity acting on some object because of the Earth, that's going to be equal to negative, and then we have the product, we have g first. It's negative 6.67 times 10 to the negative 11th, and we'll use those Newton meters squared per kilogram squared here. So let's use the units that the AP test gives. Meters cubed per kilogram second squared. Okay, times the mass of the Earth, 5.97, etc., times 10 to the 24th kilograms, times the other mass, m, divided by the radius of the Earth, 6,378,100 meters, and that gets squared. So then the force from gravity is going to be equal to negative, and when we punch this into our calculator, we're going to end up with a number of negative 9.8, and the units we're going to get here would be, let's see, the kilograms will cancel, 2 factors of meters will cancel, and we'll just have meters per second squared times our mass, m. And that ought to look pretty familiar. We've been using that equation all along. Force from gravity, or weight, is equal to gravity, or the acceleration of gravity, times m, or m times g.